So the next speaker is Athanasios Ramaila from SKA South Africa. He is part of the telescope control and monitoring team there, and he will talk about work on simulation with TANGO for SKA.
Okay, thank you for the introduction. Again, for those who have not reached out yet, I'm Athanasios Ramaila, and this is the names of my colleagues. They might be familiar. So, as part of the Indo-SA collaboration, which is collaboration between India and South Africa, we worked on developing an LMC simulation framework. LMC just stands for Local Monitoring and Control. So the outline will be as follows. So working through this project, we went through like iterations, of which I'm going to go into. The first iteration involved using some TANGO simulators within the Meerkat system, which is the current Meerkat telescope in South Africa. So this iteration involved developing simple simulators, like for example, you develop a weather simulator, and then we try to integrate it into the Meerkat system. So this was a way for us to try to learn about TANGO, since well it was new to us. So some of the learnings involved a development of a translator, which is a tool or a library that will translate a TANGO device into a CATCP, which is a protocol that is being used by the Meerkat telescope. And then we also observed that it would be actually simple for us to actually integrate the TANGO devices into the Meerkat. And then this will actually allow us to develop a framework which will help the SKA to test its subsystems within the Meerkat telescope. And then in terms of iteration 2, it involves evaluating TANGO tools, which we have observed that the TANGO community is actually a big community, and they do have like tools that we can actually use instead of reinventing the wheel. So we have looked at some of the tools like HDB++ and panic alarms. So yeah, we have seen that actually the TANGO community will supply tools that will be useful, that we can use within a Meerkat or within a radio-like telescope environment. And also translators were also developed that will take now CATCP into TANGO. So in this case, we have a CATCP protocol that is translated to TANGO so that the TANGO tools can measure on or observe the CATCP-based tools or components. And then we saw that actually it would be possible for us to integrate CATCP-based devices into the main SKA, which will adopt the TANGO control systems. And then getting into the real deal, so we managed to develop a simulator framework, which has also have behavioral extensions. Okay. So why we actually use simulated devices is that during the development of the Meerkat or Cat7, which is a predecessor of the Meerkat, it showed a very positive experience in terms of developing the whole system, so in such that we can use simulated devices during our development to do some testing as well. And also this will actually allow the SKA in general or as a whole to do some testing as they develop their system. And also this allows that you build a simulated environment or telescope environment or any system where you do your test, and you can also do some lab integrations, meaning that you can have a hardware device and a simulated device, and you can integrate them together and then be able to do some tests without having the need to actually wait for the real device to be produced. And then in terms of the Meerkat system, so it's simplified in this way. So you have 3 layers. You have the CAM components, proxies, and then the devices. So in the low-level devices, in this case, we have a fully simulated Meerkat environment. All these low-level devices are simulated devices. And then in terms of the proxy layers, this is the current system of the Meerkat, where we just replace the real devices, we put the simulated devices. Proxies are just to add a layer which will protect your devices or your lower level devices. And then the CAM components, which are the components the users can actually access. And with that, the functionality of the simulated devices are also tested regularly using some automated testing. Okay. So we managed to develop this library which will help you now to generate TANGO simulators without any effort. So how it works is, of course, you need to install it. It's available on Pipey. You just do your pip install, and then step one, what you need is you need 2 files, or you can actually use one. It's an XML file that you can generate using Pogo. Pogo is also a code generator that is supplied by TANGO, which is very easy or simple to use. It's a nice user interface where you can capture your device or system description. And from there, you have a more complex data description file, which you can capture more complex behavior or more behavioral extension to your device. And this you can use. This is where the collaboration with the Indians came about. You can use the DSL, which is a domain-specific language, which actually restricts you or kind of guides you in terms of capturing the description of your system or of your device. And then secondly, what you need, you generate an executable file. You specify your 2 data files. Once you specify your 2 data files, you just run the command simulator generator, and it will generate an executable which will be stored in a directory that you specify. And then from there, what you need, if you have already registered your devices, so in TANGO, you register your device into a TANGO database, which will remember your device such that when you run it, you just specify the executable, and then this will be the instance of the device that you are launching. Or you can use a command to actually register that for you. You just run the command and then you specify all the information, and then this will actually launch the simulator for you. So lucky enough, the library is open source on GitHub. We also have documentation for it, which is nice. And then what you get once you launch your simulator is you get a simulator with a control interface. So you have your 2 data files, or it can be 1, using the XMI, which is generated from Pogo. You feed it to your library, and then this will populate your model. It builds up your device model. From that, this will expose a TANGO device interface, which shows you attributes and commands. And then on the other side, you get a controller or a test interface for free, which will allow you to actually manipulate or poke your model. For example, you can use this for testing purposes, like say you can control a certain attribute. So what you can do is specify a certain value for an attribute, say a higher value, and you see how your device will respond. So this will be used for testing purposes to see how your device will respond or how your monitoring or controlling high-level systems will respond to such a behavior. You can also simulate some errors with that. And basic simulators, that's the one that I mentioned that you can use Pogo. Pogo is available, so free open source software that you can use. You generate a simple or a basic simulator which just have attributes and commands. And also you still get your free simulator control. Secondly, a complex simulators. Now with complex simulators, that's where you specify your device description or system description in a SimDD, or we call it SimDD, or which is a JSON file, which also you can capture it using the DSL. And with that, you can also specify like, also you get your, you can specify your attributes and commands properties within the same simulator description file. Also still you get your simulator control device. And then in terms of the layout of the JSON file, this is the layout. You have your basic attribute. You specify the name, since all the information or the metadata will be specified in the Pogo XML file. Here what you need to specify is maybe you can specify the simulation parameters of your attribute. Like you can do some signals for a specific attribute, where we're also looking at, we're looking forward to exploring simulator devices like Simulator DS, which will provide the specific signals for your specific attributes. And at the moment, we have Gaussian slew limited, where you can specify min, max, and slew rate. And then for basic command simulation, we have, so without any code at this moment, what you need, you specify what commands you need. So at the moment, you can have an input parameter command or input parameter transform, whereby you give it a value, and then it just stores it in a temporary variable. Or secondly, you have a side effect that will say this command should manipulate or should change a certain attribute of your device. And then lastly, we have an output return. That command will specifically return a value from either a variable or a attribute or an attribute. And in terms of complex simulators, here you can go further. So the nice thing about this is that now you have a complex functionality of your device. You can write an override class using Python. So here we're using the dynamic features of Python. You can specify a certain action or a function of your device, and then what you do in your simulator description file, you specify that you're gonna specify an override class, and then you just give the class name, and then once you start up your device, the functionality becomes there. So when you run your commands, it will execute the function that you provided in your Python script. And then in terms of iteration tree, we felt how useful this library can be. We said, okay, let's generate the simulator that we can actually use in a real system or in a real-like system, which is the Meerkat simulated environment. So we managed to generate a dish element, which just represent an SKA receptor. And also, okay, these are the learnings, yes. So also, we found that with this library, we can cover almost 80% of your use cases. Also, we are open up for other options that might be useful for you. And then also, the nice thing about it is also you can add some complex functionality using the extended behavior of the library. So yeah, we felt in iteration 4, we felt we need to be more practical in terms of how we can specifically use this library. So we managed to generate a dish simulator device, which we plan to now integrate into the Meerkat system. So why we chose the dish, so dish will be the first element that will be introduced at first in South Africa to be integrated with the Meerkat. So we found that okay, we can actually put one of the available models of the existing Meerkat physical model into the existing dish, and then we could use the translators that we developed to actually integrate it within the Meerkat system. So we managed to do that. So remember, this is still the same architecture of the Meerkat. What we did, we just altered this portion. We just replaced one of the Meerkat receptors with the dish using the translator, and almost, and then we added also a proxy, which I'll explain in a moment, and then everything was well integrated. And in terms of the proxy, it's more like you have a cat client. So cat client is what the SKA protocol uses. Now we want to connect to a dish. So what we do, we have this layer here, that's the translator. I'm going to talk more about it during the poster session. So if you are interested as well, please visit the poster session, and then I'll tell you more about the translator. And then we have the receptor proxy. Receptor proxy, as I said, is just a layer that kind of aggregates or protects your device from direct access, and then it allows you to do some control on that. And the simulator tools are open source, except for the TANGO translator, which we are working on open sourcing it. But if you are interested as well, you are welcome to chat with us, and then come see the poster. And then as for the paper, you can check the paper there, and I think that's the end of the presentation.